Good morning. So thank you all very much for joining us. Today we are happy to have Theo Johnson-Freyd, and he will tell us about the 3+1 dimensional topological orders with emergent fermion.
Thank you very much. Thank you for the invitation and the opportunity to tell you about this project. Before I continue, we were discussing ahead of time that some of you probably heard, I'm trying out a way to do chalk talks online. And if you have a Google account, you can follow along at your own, like flip between the chalkboards yourself by following that link that I just put in the chat. And if you don't have a Google account, I don't have a solution, sorry. And this is just because, as everybody knows, the problem with slides is you can't see what the person used to have on the board and doesn't anymore. So yes, I want to tell you about 3+1 dimensional topological orders. And I'm kind of excited about it because it's the thing I've been thinking about for the last few months. So hopefully my paper will be out maybe even this month, certainly by the end of November. The result I want to tell you about is I wrote it up, is that it's a classification theorem. The result is that there's exactly three 3+1 dimensional topological orders with only one emergent quasiparticle. In one of these, the quasiparticle is a boson, and in two, it's a fermion. Okay, so that's the theorem I want to tell you, and most of, or at least the first half of the talk will be just telling you the meaning of the words in the theorem, and then I'll at least tell you something about these three different topological orders, and maybe I'll tell you something about how I can prove classifications like this. And please interrupt with questions. It's really hard to shout at the internet, and so it's much better when people interrupt. Okay, so right, so as I said, most of the talk's going to be or at least the beginning, I want to just tell you what a topological order is. So so the idea is that is the following. So there's a vague idea, which is the following. The vague idea of topological order. I'll say some vague physicsy words, and then I'll give a mathematical definition. So the vague physics words are that you should imagine that you have some some sort of high energy, sort of microscopic theory, quantum system. And then you could imagine that somehow maybe you flow it to the IR, that in the far ultraviolet, sorry, far infrared. So that's very, very low energy, very long length scales. It might or might not happen. It might be well approximated by a topological field theory. This is a story people tell, and the way that this would happen is that maybe all of the excitations, all of the physical things in your theory, all of the so maybe all of the excitations are heavy, and in the far infrared, in the very low energy scales, they're too heavy to move around, so they just sit still. And then if there's no light particles to be able to measure, if there's nothing that's sort of low energy that can measure how far away things are, and if everything's just locally constant, then it's essentially topological. So being very heavy, you should think of as meaning that something's locally constant, that the Hamiltonian is zero. That's the sort of the symptom of being topological. And topological order is an attempt to that this is an attempt to axiomatize. This is supposed to axiomatize basically the topological field theories that arise in this way. And the history is really from people thinking in about 2+1 dimensions of what particles arose. When I say quasiparticle on the previous slide, it's because physically you might have a microscopic description that has some particles, but in the far IR, those particles might behave. They might compile into larger, more complicated particle-like objects that then, in this kind of effective theory, behave like particles, or strings, or whatever they be. So that's the vague physics words, and then it's called order because back in the 20th century there was a picture of phases of matter that involved order and disorder, and the idea that maybe something in the far IR would be ordered, maybe because it would crystallize out, maybe there would be some disorder. And this was an important part of the classification of phases and of kind of with sort of symmetry breaking classification, kind of lambda classification. And then it turned out by the late 20th century that there were other types of order that weren't crystalline order. But the history here is that I just wanted to mention the history, that this word order here is you should think of like other types of order or disorder, crystalline order or something like that. And so in particular, topological order is very worked up or I think the idea is that it's eventually going to replace certain notions of symmetry. It'll subsume older ideas about what symmetries of phases and a lambda classification of phases. So that's the idea. So let's try to axiomatize what you might see in the physics. And let me also just, so let me try to give let's list what you would see if you were looking in the IR in a topological field theory. If you were looking if you had some physical system that was approximately topological, what would you actually be able to do with it? So you have in an approximately topological. I'm sorry, my iPad, my pencil seems to have run out of juice. Technical difficulties for a moment. I charged the iPad, just didn't charge the pencil. Let's see if this will work. So what would you have in an approximately topological, and I want to emphasize this is sort of an effective field theory. Well, the first thing you might have is you might have some, so by what do you have, what I really mean is for instance, what operators do you have? For instance, well, one of the things you might have is you might have vertex operators. You might have operators in your theory that project you, where you can insert them just at points in space-time. Another technical difficulty. And go away, cat. I'm trying to give a talk. You might have particles, and so the vertex operators. Let's see. So it's a topological field theory. The vertex operators in a topological field theory, except for in very low dimension, these will be some associative or maybe commutative algebra. Associative algebra in 0+1d, or commutative algebra in greater than or equal to 1+1 dimensions. Again, it's commutative just because everything's topological. Particles in a field theory, the way you talk about particles is you really talk about the world lines of particles. A particle is a one-dimensional extended operator.
So when you said
Yes.
commutative algebra, will it also have like extra structure as you get higher dimensional, that just more than being commutative, or?
No. It's just a commutative algebra.
I
There's
thought it was,
very
I thought, right, like once it was like there were two codimensions, it became like an E2 algebra or something like that, whatever.
Yeah, but it's just a vector space. There's no interesting E2 algebras if you have a finite dimensional vector space.
Okay.
Theo, I have a short question.
Good.
When you say order, is in solid state physics there is a notion of a phase. It's like
Yes.
a phase of, there is a ordered phase, disordered phase. So it's the same thing.
Yes. Well, so what I was hoping to do was motivate a definition, or I could just give a definition. The idea is the following. The idea is that the thing I'm trying to motivate a definition for is supposed to capture the phase of topological matter, the topological phase, the gap topological phase.
Okay.
So let me go back and let me sort of, rather than motivating it this way, let me do this by example. So maybe I'm going to sort of, since I didn't decide how the order I was going to say things, and maybe I'll give the definition, and then well, let me sort of, as an example that I want you to keep in mind, sort of to keep in mind is something that I think maybe is due to Kolya, which is that the modular tensor categories are basically what you have in 2+1 dimensions. 2+1d topological order. So this is basically the Reshetigan-Turayev construction. That's if you ever sort of decide to zone out for a moment, that's what I want you to remember for about topological orders. So what I was going to try to say is the following. What I was going to try to say is that in a topological order, in n+1 dimensions, what you have, well, or at least you might have, well, you might have some n-dimensional extended operators. You have extended operators. You have operators of various dimensions. Operators are not something mysterious. Operators are just some modification you can make to the field theory, to your system. So for instance, you might have Wilson lines for a gauge field. You might have world lines of particles. In fact, anytime you have a line, you should think of it as a world line of a particle, of quasiparticles. You might have world surfaces of quasi-string excitations. Etc. And the first thing I want to observe is that these objects form a higher categorical structure. So for instance, in particular, if you have any extended, how do I want to say this? So for instance, the n-dimensional operators in n+1 dimensions, well, those, maybe my n is going to be 2 for the pictures. An n-dimensional operator is something that can insert along a surface, an n-dimensional, a codimension 1 surface. And if you could take 2 n-dimensional operators and insert them next to each other, and then you could zoom out. Everything's topological, so that doesn't do anything. And there's a fusion just from rescaling. And so what you learn is that the n-dimensional operators in an n+1 dimensional theory, these have a multiplication, a monoidal structure. And by the same token, the n-1 dimensional operators have a braided monoidal structure, and so on. And so at the end of the day, the axiom that I want to sort of what you see from analyzing this is you find out that the full operator content is monoidal n category. Maybe I'll call it A of all possible n-dimensional operators. The n-1 dimensional operators, what is an n-1 dimensional operator? Well, an n-1 dimensional operator.
Sure.
Yes.
I'm trying to recognize all this.
Yes.
For n equals 2.
Okay.
What are the, in Chern-Simons, what are the surface operators?
Let me tell you a statement in 2 slides, and then you'll, so the thing I'm actually about to say is that in most examples, there are no interesting n-dimensional operators.
Okay.
Or rather, they can all be, there's a sort of systematic way to reconstruct them.
Okay.
So there are n-dimensional, there are surface operators in Chern-Simons theory. It would be, you could say a Chern-Simons theory is given by a modular tensor category, and a surface operator would be fusion, well, what is a surface operator? A surface operator is something you can insert on a surface. That's the definition. So if you have a modular tensor category and you can ask what are the ways to go from on a surface from a modular tensor category to itself, that's the same as folding it over and asking for boundary conditions for the folded theory. So Collier asked in Chern-Simons theory. So for example, in Chern-Simons theory, the surface operators are, so first, or maybe I'll just say in general for Rezhetik and Sarayev theory, for some modular tensor category, the surface operators are boundary conditions for the m times m bar theory, which is to say their fusion categories with center n times m bar.
Okay.
N times m bar.
Mm-hmm. Okay.
And then there's some systematic way that you can recover those. Well, those are actually the same as just categories with an action by m, because this is a Drinfeld center. And so because this is a Drinfeld center, these are also the same as just algebra objects, maybe braided algebra objects. No, excuse me, algebra objects in optimum rate equivalence.
But to formulate what they are locally in terms of Chern-Simons theory, it's difficult.
So the thing that I was about to say was that by when you write down these axioms, you can prove that they're just algebra objects in M optimum rate equivalence.
Mm-hmm.
And then what is an algebra? Well, an algebra is some collection of strings, of objects with some multiplication. And so the surface has a microscopic description as a network of world lengths. So okay, so I'm sort of going slower than I meant, and I'm getting away from the thing that I wanted to, the theorem I wanted to tell you. I should have just, well, I could have just told you the definition of what I was doing, and you would have said, that sounds like some interesting category theory, where's the physics? So now I'm trying to do some interesting physics, and you're going to say, where's the category?
Oh, very good. Sorry, I will not.
No, that's good. So the definition that I was trying to build up to is the following. So the thing I want to get to is this is a difference between having. Yes. So here's the first definition. So the definition is that an n+1 dimensional topological order is an monoidal n category. And there's some niceness conditions. When I say category, I really mean linear and Cherubi complete. And I wanted to satisfy two properties. It should be, well, there's something that anybody who studies topological field theory won't be surprised about, which is that it should be should have some good dualizability properties in an appropriate Morita sense. I won't spell that out right now. But it's not, I mean, I can axiomatize it completely for you. And this you should think of as being meaning it's a multi-fusion N category. And then the other axiom that I want to say is that there's a what's called remote detection. You need to go away. What's called remote detectability. So maybe I'll call this curly A. Remote detectability, which says that that the Drinfeld center of A. So the remote detectability says you should be able to detect any operator by doing a measurement. The way you detect things in an associative algebra is with a commutator. And so the remote detectability says that the center, the Drinfeld center of A, is trivial. And then the thing that I want to, the theorem I want to say, the first theorem is that actually you can simplify this. So if you have an N category, you can take the endomorphisms of the unit object. And I'll just say it this way, that if you are actually fusion, so meaning that the unit object is indecomposable, so it doesn't decompose as a direct sum. So why would you care about that? This is saying that there's a, physically this is saying there's a unique local ground state. Then A is recoverable, is recovered from the braided fusion N-1 category of endomorphisms. I'll call it omega A. So my notation is going to be that omega A is the endomorphisms in A of the unit object. So just to repeat the definition, an N+1 dimensional topological order with a unique local vacuum well, if there's an equal, so it's a fusion category, is the data is braided fusion N-1 category. And then there's still this, this remote detectability hypothesis. So the braiding is non-degenerate. There's a sort of an, you could think of this as a modular tensor to n-1 category with non-degenerate braiding. And literally that means that some center is trivial, where now this is more like a Muger center. Okay. So I've used about half my time giving just the first definition, and I didn't get to say the next thing. So what am I trying to do? So in the very beginning of the talk, I said I was interested in the case where n was 3. So then n-1 is 2. So I'm interested in braided fusion 2 categories with trivial braided center. So this means like basically the braided or kind of Muger center. And anyone who's studied Reshetikhin-Kudryaev theory will recognize modular tensor category here. That a modular tensor category, except that I'm leaving out something about ribbon structures. If a unitary modular tensor category, the ribbon structure is determined by the rest of the data. If you're unitarizable, then the unitary structure is canonical and the ribbon structure is forced. So you can leave out all discussion of ribbon structures and just do algebra. Like it's justified to do that. And then I'm saying that a modular tensor category is essentially a braided fusion 1 category with a non-degeneracy condition on the braiding. And I'm just converting 1 to 2 for the problem. So that gives the first word in my slide. I told you I was on my theorem. I was classifying 3+1 dimensional topological orders and with some property. And then the next thing I said is that I care about the case with a unique. So what are the quasiparticles? Well, if you had a braided fusion 2 category, the particles. Now from here on out, I'll just do the case that I care about, which is in 3+1d. The particles are the category of world lines of particles anyway, is the category of endomorphisms of the unit object in B. So this is automatically a symmetric fusion category. I guess, and because I'm in the 3D. And I said I wanted a unique non-trivial particle, so I've now there's an exercise for the audience. How many symmetric fusion categories are there with only one so of course there's the identity particle, identity object, but how many symmetric fusion categories are there with only one simple object other than the identity? If I were in person, I would actually glare at somebody and make them answer. Okay, so the symmetric fusion categories with simples, just one object and one other, the identity and one other object are well, there's super vector spaces, and there's representations of Z2. And the difference is that in this particle, so this is my emergent quasiparticle. And the difference is that in S2, X is a boson. And in supervector spaces, X is a fermion. And in either case, it squares to the identity. Let me not call it X. For some reason, I would like to call it E because I'd like to think of it as an electron. While my pencil charges again, is there any questions right now? So,
but these examples are n equals 2 still, not n equals 3, or is that?
I'm talking. I'm I'm going to go back to the context of my slide where I'm talking about 4-dimensional, 3+1 dimensional theories.
Mhm.
So 3+1 dimensional theory, to repeat, is the data of a 3+1 dimensional theory for me. If it had multiple ground states with something about fusion categories, because I sort of needed to tell you that to give a kind of mathematically correct story.
Yeah.
But what I'm ultimately interested in classifying are braided fusion 2 categories. And then anytime I have a braided fusion 2 category, one of the things I can do with it is to look at the symmetric fusion 1 category of endomorphisms of the unit object.
Okay. So you're saying, like, as a first step to classifying these two categories, you can just sort of look at that one category. Okay.
So let me remind that, so B is going to be a braided fusion 2 category. And omega B is my notation for the endomorphisms of the unit objects in B. And it's always one category lower and one monadality more. So since B is braided fusion, since B is braided, omega B is going to be whatever the thing after braided is. I think it's called selective, right? E3. But it's just a one category, and E3 things that are just one categories are automatically symmetric. Okay. So let's try to do the, so what do I have? So I have, I have a non-degenerate braided fusion 2 category B, and it has a, as I said, I have the endomorphisms of the unit object. Let's try to the case where it's representations of Z mod 2, so an emergent boson. So I'll think of the objects in here. The simple objects are just the vacuum and a particle I'm going to call E. The electron E is an emergent boson. It's some I'll repeat that if I add a microscopic description, then microscopically, this thing that I think of as a particle in the low energy is actually some very complicated combination of excitations microscopically. But in the low energy, it's behaving just like a heavy particle. And let's try to classify these. Well, there's a trick. There's a strategy. So I'm going to follow a strategy of Lan, Kong, and Wen, who basically said how to do these from a couple of years ago. And they said the following. They said, let's take whatever our original theory, we have some mystery theory B, plus 1D theory B. But because I know that the field theory is I know what the particles are, I can build from this what somebody who studied kind of modular tensor categories will recognize as a condensable algebra. So you look at the condensable algebra. Well, the way you really do this is you look at the fact that there's if you look at the fact that inside of here, well, this is you should think of this really not as, I should have called this really I should have called this rep Z mod 2. So E you should think of it as like it's charged under the set. It has non-trivial charge under the Z mod 2. And well, inside of rep Z mod 2, there's a commutative algebra, which is the functions on the group Z mod 2. Doesn't matter that I'm doing Z mod 2 right now. An asymmetric, if you have the representation category of a finite group, it has an element, an algebra called the functions on the group. This is a commutative algebra object. And if you studied Tanakian duality, this is the algebra object that you could reconstruct from the fiber functor. And because it's a commutative algebra, and in fact, it's better, it's a semi-simple commutative algebra, you can condense it. So this is the information that you need to write down this is what you need for condensing. It's condensable. And what that allows you to do is it allows you to condense it. You get a wall, which is what, I'm not going to try to explain what condensation is really physically, but if you have whatever a condensation is, it's some procedure that you do where you modify the Hamiltonian in some systematic way, where you force some particles to really freeze out. And so you could run that procedure in one part of your laboratory and not in the other part of the laboratory, and sort of turn off the procedure slowly. And after zooming out, turning off a procedure looks like a wall. So you get some wall from the original mystery theory B to some new theory. New 3+1d topological order in which the particle E is confined. And maybe I'll call it, I don't know, B prime. It's another modular tensor category. And I'm saying this all sort of in the physics language, but I want to emphasize that this is really a procedure just in the worlds of fusion 2 categories. This is something you can do purely in category theory. Given an algebra object, you can, in a symmetric monoidal 3 category, in a like this, you can build a new theory in which you condense it. Well, this is a new theory, B prime, and it has the following property. It has the property that the endomorphisms of B prime is trivial. And now I need to use a non-trivial theorem, which is that, maybe I'll write it in black so that you can really see that it really shows up. Which is that so the lines are trivial. So the theorem is that 3+1d topological order with no lines, that this theorem is that this forces B prime to be the trivial theorem. And now, so what you find out is you find out that whatever your mysterious theory B was, you can always write it you can always find a boundary condition for it. And the boundary condition that you can find is, so there's a more general statement that says that anytime, so using this technology, you find more generally that anytime you have a topological order in 3+1 dimensions where the lines are rep G, you can always find a boundary condition. You can always condense it to the trivial, the vacuum theory. And well, I only have like maybe 10 minutes left, so I won't tell you all details of how this works. But this really uses this statement about the center being trivial. The actual statement is that if there's no lines, then, well, anyway, ask me afterwards. There's a beautiful separate story about this theorem. So what you find out is that that the punchline of all of this is that if you have a 3+1d topological order, which is to say non-degenerate graded fusion category, graded fusion 2 category, and if the lines in B is rep Z2, then B has a boundary condition. And if you have studied Reshtikin-Turayev theory in 2+1d, you'll be familiar with the statement that if you have a modular tensor category with a boundary condition for the 2+1d theory, then that modular tensor category is actually a Drinfeld center and comes from Turayev theory. So then B is actually the Drinfeld center of some monoidal 2 category. And you can even work out what that monoidal 2 category is. The way you did the construction, the thing you used to condense it had a Z2 symmetry. And so this monoidal 2 category is something about Z2. And then, so actually B is our original theory is a digraph-Witten theory for Z2. There's only one of those. Digraph-Witten theories are measured by group cohomology, and that's trivial in this degree. So B just is basically a toric code. I talked all about the easy case, the bosonic case, and I have maybe 5. How much longer do I have? 5 or 10 minutes?
And that's up to you.
I have until people disappear. Maybe I have until people decide they give up on me.
No, you definitely have 10 minutes. Wait a second.
10 minutes. Okay.
Yeah, it's its own.
So what I really wanted to do was tell you about the case with the emergent fermion. And in that case, so the more interesting case is where I have again where my the lines in my theory is a copy of super vector spaces as a symmetric monoidal category. And so you could ask, can we classify topological orders with this case? So this is where, so that again, I'll call my objects 1 and E, but now E is a fermion. And to do this classification, I have to use another step. So to do this classification, I'm going to do the following. What I can do is I can so what I want to say is the following. You know, any symmetric. So I want to remember that something that we learned from that sort of underlies the theory of Tanakian duality, which is that that every symmetric monoidal category is trying to be the representation theory of a group. And it succeeds exactly when all the elements are bosons. And otherwise, it's almost the representation theory of a group. It's the representation theory of a group, except for some super phenomena. And so what the idea is that instead of thinking of super vector spaces, I want to think of this, I still want to think of super vector spaces as being like rep Z mod 2. But it isn't. I need to sort of think of it in a super world. And so what I can do is I can do it in 2 steps. The first step I can do is I can kind of do the classification over super vector spaces. And it's like saying I want to classify. Here's the analogy I want you to think of. You might have wanted to classify something over the real numbers. And it's much easier maybe to classify it over the complex numbers and then argue through some Galois descent to the real numbers. So by this, I mean literally, I mean classify, I mean study the braided fusion to super category. that I will just, since I don't have time to say what I mean, I'll just write it as B tensor with SVEC as a supercategory, whatever that means. And it's non-degenerate in the sense of super braided fusion 2 categories. And then the second step is to study the Galois descent problem. Along the inclusion of VEC into SuperVEC. This is like if we wanted to classify, say, real, if you had wanted to classify real semi-simple Lie algebras, you might classify complex semi-simple Lie algebras and then ask for real forms. Ask for complex and anti-linear automorphisms of order 2. So basically exactly the thing I told you before goes through for the first step. So the first step is just, this is just as before. You run the classification and you find that B supervec ends up being an appropriate Drinfeld center. It's just basically a Z2 gauge theory. And there's only one of these. Just from a cohomology calculation. And the interesting thing is this Galois descent problem. The Galois group here is, well, it's a fun exercise. Ask yourself, what are the automorphisms of supervector spaces as a symmetric monadal category? Well, there's only one automorphism. I mean, there's only the identity. Every automorphism, every symmetric monadal automorphism of supervector spaces is trivializable if I'm working over the complex numbers. But the identity itself has a monoidal automorphism. And so the Galois group here is not Z2, but it's kind of Z2 shifted by degree. It's sort of a BZ2. So a physicist would call this a one-form symmetry. So Z2 in degree 1. So since I'm short on time, I'll tell you the final answer, which is that the final answer is that up to conjugation, I mean, there are two, I'll say it this way, there's sort of two kind of bosonic forms of basically 3+1d Z2 gauge theory. So what I'm saying is I'm telling you a classification of ways that that you can give Galois descent data, of ways to find a one-form symmetry group acting on this theory. Let me say it better. So there are two ways that Z mod 2, that a Z mod 2 one-form symmetry group can act on this theory, which was basically Z2 gauge theory. Let's see, supervec. Satisfying some conditions that make it sort of take you down to a bosonic form and preserve and keep the electron be a fermion. So cutting out a bosonic form. And in one of them, the sort of Galois group, think of this as a as a Galois group. And my pencil's out of juice, I'm sorry, but my time is out anyway, so I'm going to say this in words while the pencil recharges. In one of them, the Galois group acts without a gauge and a Tooft anomaly, and the other one it acts with an anomaly. And I wish I had time to tell you what those meant. So this is sort of the Galois group. My pencil's out of juice. I can't keep telling you this story with that. How much time do I have? -2 minutes? What do I have? 2 minutes?
No, it's 2 minutes. Yeah.
Okay. So let's say this is basically, yeah, well, it doesn't matter. I can't keep writing on the screen because apparently these don't have an infinite battery life. Little did I know. So in one of them, the Galois group acts within a Tooft anomaly, and the other it does not. And what I had planned to tell you before I got distracted myself by trying to give complete definition, by trying to give a sense of the definitions, was a bit more information about these individual, sort of the structure of these specific braided fusion 2 categories. And I can list. So by doing this sort of these calculations, you end up being able to just exactly list all the operators in these theories. So maybe I if I can, let me try to say this. So the Galois group.
Theo, can I ask you a question? Operators in this theory, how they correspond to objects or to?
Yeah. So let me tell you what you get at the end of the day. And I will just go a minute or two over time, and we can use up some Q&A time if that's okay.
Okay.
So what I wanted to do was tell you, so at the end of the day, you do this whole classification and you end up with you do this whole classification and you end up with 3, I told you that there were 3 interesting, and the 2 most interesting ones are these ones there are 2 non-degenerate braided fusion 2 categories.
Theo, you should use letters that are 5 times bigger.
5 times bigger. Okay.
Theo,
This
can you stop screen sharing from
Yes.
iPad, please? So we can
sorry.
see your video.
That would be much better. Okay.
That's great. Thank you.
Great. This is why I have a chalkboard. It's because because the iPad almost worked. So what I wanted to do is tell you about these 2 braided fusion 2 categories with particles 1 and e. And so what I want to say, and I maybe should have just, well, maybe if I go another hour, I'll just tell you about these. People will leave. I'll explain these 2 examples. So all I want to say about them is the following. I want to say that there's these 2 interesting braided fusion 2 categories like this. So what is a 2 category? A 2 category has there's some simple objects. I'll just tell you all the objects, all the simple objects. So the 1 morphisms I told you already, there's 1 and there's a particle E, which is a fermion. And the E particle is a fermion. And that's true for both of them. The objects, there's actually 4 simple objects, and each of these has, say, C many endomorphisms. And each object, there's kind of 2 classes of objects. One of the most interesting parts of 2 categories that's different from 1 categories is that in 1 categories, like an object is, the Schur's lemma tells you that the two different simple objects don't talk to each other at all in a semi-simple one category. Because if you have a map between simple objects, well, if you have a map from a simple object to something else, or between simple objects, and if you have a map, it realizes kind of, you can like, basically the reason why they don't talk to each other is because you can always take orthogonal complements. In two categories, this is no longer true. Simple objects can still have maps between each other. They can still talk to each other. And rather than thinking about all of the objects, it's also useful to think about kind of the components are the sets of objects modulo which objects talk to each other. So what it turns out is that there's those four objects. There's a vacuum object, an object that you get, which is kind of an object that you get from condensing. There's some object that I'll call capital E that you get from condensing the electron. And then there's kind of two other objects that I'll call M and M prime. And to answer Kolya's question, the E is a one morphism. So this guy has a world line. It traces out, it's a particle. It traces out a line in 3+1d. The objects of my two category, those are surfaces. So these things trace out surfaces. I'm telling you all this for both of my categories at the same time because it's almost exactly the same. And what I wanted to tell you is really, I wanted to tell you how to see the difference between these two guys. So this line here is electrically charged. It's an electrically charged particle under a sort of Z2 gauge group is how you should think about it. These two, so these guys trace out surfaces. These two magnetic strings, you should think of them as magnetic strings. For both of these categories, there is a symmetry, automorphism, D that switches the two strings. I should tell you the fusion rules. Squared is isomorphic to 1 because it's a fermion line, it squares to 1. This electric string, you should think of this as like a kind of cliff 1. And it squares to 1. Everybody squares to everybody else. I mean, the magnetic string squares to 1. So there's the fusion rules. And all I wanted to tell you was the difference between the two categories because it was this thing about anomalies that I ended on, which is that in a sort of non-anomalous of the two different categories I can construct. In the non-anomalous one, I want to say this. The magnetic strings in both cases square to the identity. In both cases, the magnetic string, okay, I'm in a braided 2 category. If I have an object, a surface operator in a braided 2 category, I can cross it over itself and ask what's the value of that braiding. Just like in a braided 1 category, I can cross an object with itself and ask what's the value of that. That value will be some line operator, or rather it'll be isomorphic to some line operator. And it turns out that the self-braiding, if you take an M surface and cross it with itself, that self-braiding is isomorphic to the identity. You have to choose that isomorphism. There's some choice there, but you can choose this isomorphism, and the choice ends up not mattering for what I'm about to tell you. And then the last thing to say, so because I'm in a braided 2 category, I have an object which squares to itself, and its self-braiding doesn't generate anything else. So that means that this whole braided 2 category contains a braided sub 2 category which is just sort of supported by M, with objects just 1 and M, and one morphism's just the identity, just trivial. 2 morphisms just C. And then the last thing you can do is you can ask what is this braided sub-2 category like? And braided sub-2 categories, braided 2 categories with Z2 fusion rules are classified by they're classified by the 5th cohomology of KZ2 with C cross coefficients. And anybody who's calculated those knows that that's a Z2. And it's the difference between these 2 categories. Okay, I'm well over time. This is what I wanted to tell you. There's these 2 categories, and it's really hard to tell them apart because almost all of the data of the 2 categories looks the same. And you have to look very carefully at the self statistics of the magnetic string to tell them apart. So thank you for your attention.
Thank you. That's yeah. So, any questions? Theo? Okay, so
we had a bunch in the talk on
yeah,
over time, so probably people left. But
so that's we have a bunch during the talk. So thank you very much for joining us. And
sorry for going over.
That's no problem. Just and that's.
Thank you again.
Thank you. Oh, by the way,